My name is Joseph Wunderlich. This is a review for the second part of multiple parts in a high-tech course called Embedded Systems, or Digital Design and Embedded Systems. This is my website in the high-tech. And this course. This is the syllabus. We're in here, and I'm making this video right here. So previously, the students learned about steps, my 8 steps of combinational circuit design, and defining the problem, creating or encoding variables, creating truth table, simplifying the functions, logic circuit, maybe convert to NANDs, chip circuit diagram, and then addressing assumptions. Now we're deviating from that with some ad hoc design. So all this up here is done, and we're in here now. And firstly, a 2-bit adder. And this is the old, using the rules that we just showed above. We have two input values, and you create a circuit and block diagram and a truth table, and then maps. And it's just going to not scale well if you have more than 2 bits, and that's what the point of showing this example. And then we talk about a bit slice is a scalable way of doing it, and with 2 slices and 4 slices, and then design the bit slice. And then we looked at this here, which is what you would get by designing the bit slice for a full adder without further simplification. And then the textbook says that's the equivalent of this, but we want to prove that to ourselves. So we prove it in 3 ways using tables and maps and algebra. And there's a table way here, and we show how that works. And the way that works is that this equality, how can this be equal, these 2 sides, when ORing these 2 together is not the same as exclusive ORing. And so we look, and what happens is the part of the equation that is the OR of XO, YO carries the day. That makes that work. And we had looked at that before in the previous review. And so a more clear example of that is this, which I made. So if we have bit slices here, the half adder would be here, and that is a useful function block in itself. And then we have these full adders, which you just saw designed again here, a full adder. And then again, how can that simplify? And then we see these homework assignments that show that even though this part and this part really are not equal, the OR XO YO on both sides will carry the day in the cases where those 2 are not equal. And the way that manifests itself, or the proof of that, here's homework problems of the past. There's the table method again. So this is again that showing that in the case where they are not equal, these YX carry the day. Also show that algebraically here by expanding both sides of this out to canonical form. Canonical form is where you have all the product terms, every combination of three variables that the equation yields a 1 on both sides, or canonical form is all the 1s. Yeah, and then also you see here, and out in the mapping proof of it, if you were to map both of them, you see that it results in the same 1s on each map for both sides of the equation, even though the groupings are different. So again, the full adder simplified using ad hoc simplification methods. First designed with the standard ways of designing, but then an ad hoc simplification gives you that full adder. So next we go into subtractor, and the same thing, starting out the old way of having a 2-input subtractor, where now you have differences and a sign bit for, so you're borrowing when you subtract two numbers. If one, if the y is bigger than the x, you need to borrow. And so you borrow from over here, the sign bit is going to go negative. And so that sign bit is an actual output and maps for that. And then a half subtractor and a full subtractor, the development of that as a bit slice of its own. And then we say, wait, stop, let's not do this. Let's instead use our knowledge of 2's complement and make something like this. And it's a little messy here, so we're going to look at it in a more cleared up version that I made. So we go to the ad hoc adder subtractor here. And ad hoc means, by the way, when done or created for a specific purpose, sometimes deviate from normal rules. In our case, our combination design circuit rules, and my 8 rules. So we have this situation where, all right, we know how to design a full adder. We know how to cascade them together for n-bit wide adder of x and y. But what about subtraction? So for subtraction, we see that we can use 2's complement. And what is 2's complement? 2's complement is, at first we need to look at that, but it means to make a negative number, we toggle the value and add 1. And that will make a negative number. What we want to do is use the same device for both adding and subtracting. So to add, we just want to leave it alone, and we'll have a control bit coming in. It says leave it alone. Subtracting, we're going to have a 1 coming in. We're going to use that 1 to create a negative number out of y. So in effect, we're adding negative y. And so we want a 2's complement for that. So we'll just take a second here and look at 2's complement. So 2's complement is whenever you want a negative number, you toggle and add 1. So there's examples of that. So I won't go through that here, but if you don't understand that, you should stare at this for a while. And if you forget your number representations and how that works, you should go into here. Just important things in here. Don't dwell on the ASCII and the floating point things that are in here, but do look at Just make sure you understand how to convert from binary to decimal and decimal to binary, because you need that as part of just doing two's complement. And then the floating point, again, don't worry about all the floating point in here. That's not part of what we're doing right here. So again, we're doing this ad hoc adder subtractor. And the idea here is to leave the whole thing alone when we're adding numbers together. So the control bit is telling this giant device here whether to add or subtract two 4-bit numbers in this case. And we can scale to n numbers with two 4-bit numbers here. So the control bit, if it's 0, we want it to do nothing. And when it's 1, we want it to do 2's complement. So we don't know what to put here yet. These exclusive ORs we don't know. So we're figuring out what to do. And so we take y and the control bit, and what we want to do is something to y. So what would it be if the control bit's 1? So y and 1. So when y is 1, we see, oh, look, it's toggling it. When y is 1, look, it's toggling it. When the control bit is 0, y is left alone. When the control bit is 1, we toggle y. When the control bit is 0, y is left alone. When the control bit is 1, we're toggling y. So that's part of the two's complement. We can see that, okay, what is this? Well, this happens to also be an exclusive OR gate. This is the behavior of an exclusive OR gate, where exclusively one of the inputs is 1, and we get a 1 out. So, okay, this will help us toggle, but we still need to add 1 to get 2's complement. Well, if we use an exclusive OR and stuff the control bit into the carry in. Now, the control bit stuffed in as a 0 when we were just adding is great using full adder. Like, we're not using a half adder here, we're using full adder. So when we just want to add, we need the carry in to be 0 here. But when we subtract, we're toggling and adding 1. So we want to toggle by putting exclusive OR gates with the y, as it found to be down here, and we stuff a 1 in, and that's our adder subtractor. Next, we want to look at a multiplier with ad hoc, using ad hoc methods. So firstly, we just make a block diagram. Okay, what's going on here? We want to do a 2-bit and two 2-bit numbers coming in here of x and y. You could put a little indication of 2 bits here, but 2 bits coming in each of these lines. What's coming out? Well, let's look at the worst case to figure out how many bits we need. How many bits do we need coming out? Well, 1, 1 is the worst case of two bits, which is 3 in binary. So 3 plus 3 is 9. 3 plus 3 is 9, and therefore this is 9 in binary when we're multiplying. And so we need 4 bits coming out. We need 4 bits coming out. All right. Well, for ad hoc purposes, let's just put it out in long multiplication. Just see what this is how you would do. You learn in grade school multiplication. Here's 2 2-digit things. And so this value is this times this, and then this value is this times this, and this value is this times this, and this value is this times this. Yeah. This value is this times this value is this times this. And you shift over when you do the here. And then you have to add all that. And then you say, okay, how can we do something ad hoc? Well, first, how do we do a 1-bit multiply? Well, let's make a little table. X of x and 1. If it's 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. What does that look like? Well, that's an AND gate. That's an AND gate. So we can replace now all of these multiplications with AND gates. And then here's our product terms coming out. So we have to figure out how to add all those together. But we figured out how to do part of it, this 1-bit multiplication. Now, what about these parts here, the additional parts? Well, we can just say that this ANDing can go right to P0 because there's nothing, it's not adding to something. So this AND gate can go right to P0. Then we have to add this AND gate to this AND gate. Okay, so let's that AND gate to that AND gate. How do we do that? Well, let's use one of our functional blocks. If you recall the half adder doesn't have any carry in. It's just 2 bits. And so here's 2 bits. That's a good use of the half adder. And it has a sum coming out, which is our product term here, and a carry out. And then, okay, fine. Then we need to do the next column, which is this one here. Now that has the carry from adding these two added to this. And so we have that going, here's the carry added to this. And we use a half adder again, because again, it's just a 2-input adder. We don't need a 3-input full adder. This is a 2-input half adder. And then the product term comes out and the carry comes out. So this is ad hoc. Now, in this case, I put the old school with rules way second, just to show, okay, what if we had done this the old way? This is my own scribble notes got lost on this. So I found this online, somebody else, but this is what it would look like, where you have 2 2-bit quantities and you multiply them together and you make maps and equations. And then that's not very scalable. But now we see that scalability of, here's a scalable version of the initial ad hoc design, a little bit different, but the same kind of idea. Then we have in this area here, we're doing review, functional blocks. So here are all of them that we know so far, without looking at the internals, just the half adder on how that behaves, a full adder, how that behaves. We discovered that a 1-bit multiplier is just an AND gate, so I put that on here. Here's an n-bit adder subtractor, a 2-bit multiplier, so we just did all those. And then we have some new ones here. So a decoder now works like this, without showing you how the internals work. This is how a decoder works, and this would be for like the opcode of a machine code, 2 bits coming in and 4 different things coming out. A multiplexer where you pick which one gets through, which input signal gets through. And we looked at this already in class, so that should make sense here. And we have a select bit now, which is an input, a 3rd input. So you have 3 inputs determining what's coming out of A. And this would be routing data in the computer, for example. And then an encoder, a priority encoder. And this one's a little trickier, where a bunch of peripherals are asking for service and which one has priority over the others. So in this case, W here is 1, indicating has the highest priority. And we don't denote that by, we don't care if the other peripherals want service. If one wants service, it gets that service. And then this is a code we made up to show that, okay, 1 will tell us W needs service, and also a valid bit here for the case where nothing is wanting service. And so we get this kind of table here. Again, not designing the insides. This is something you can just get out of libraries and logic simulators and buy as chips and use as a functional block as you build in bigger things. And then another one, another functional block is a demultiplexer, in this case for routing X somewhere. And this has 2 inputs, the signal that needs to be routed and which way to route it. And then we have an inactive, and this is how it's a special a symbol that's used in the data spec sheets that you can see for if a signal line is not being used, it's inactive, but usually logic 0 because it's connected something, and you don't typically want to leave a floating pin without a logic 0 1, just a disconnected line is not necessarily logic 0. It can pick up random signals that you need to actually tie it to something. So they'll say in the spec sheet what it does. And then the insides of some of those, here's the inside of how to design the insides of a 2x1 multiplexer, 2 inputs coming in, 1 coming out. So you just make the table, and so now you can see how the insides are designed with that. And then for a 3x8 decoder, 3 inputs, 8 output decoder, and how that looks. And only 1 signal on the output is going to be high. So you really don't need the maps here. And if they're asked for, you should do them anyway. But there's no map simplification because only one min term for each of these permutations of input variables. So you can circuit like that. And so again, that is the summary of this part here, where we deviated from the steps up here and made combinational circuitry. We're still combinational circuits, but ad hoc. We used a little bit of our Boolean algebra knowledge here to help us see how to simplify some things. And in this class, we don't do a lot of this. Now it used to be a major, several week parts, a couple week part, but now we've moved that into a discrete math part. But we still use some Boolean algebra to see ways to simplify circuits other than our mapping techniques, which we do all the time. But the algebraic one we only use occasionally, as we had seen in simplifying the full adder circuit. So now we'll move on to sequential circuits, where there's not just inputs and outputs. So this is leading this segue into the next part. So we just did all this stuff in the box here, which is combinational logic of inputs and output stimulus, but no memory. And so we're going to go down to sequential circuits where there's memory and feedback, and how the circuit responds is not just a function of the present input stimulus, but also past. And that's the stuff of making a finite state machine that drives the pipeline sequencing of machine instruction cycle execution in the pipeline stages of computers. Okay.